we have learned about strain transformation in the last class, and we saw that it's not different from stress transformation. Today we are going to use Morse circle. What we have used for stress transformation will be used here also for strain transformation. Okay, I'll quickly finish today's class, and then probably if I get some time, I'll show you some videos regarding this. Okay, these things what we have discussed in the last class. What are why do you do strain transformation, what angle we take, what is the positive side of the angle, and how do you draw deformed diagram. So here also I have given one complete slide for how to draw deformed diagram for your explanation. So this is what we got, that stress sigma x becomes epsilon x for your formulation that you have. Only thing that changes is tau xy in stress converts to gamma xy by 2 to make it tensorial strain. And the equations to convert transform from one plane to another plane are also similar. As you can see, epsilon x1 and here gamma x dash are stresses and strain in a deformed in a transform coordinates, and you can see the relations are almost similar except for gamma xy, which is always will be the case. And there is one invariant which you need to know. The invariant is, there are two invariants actually. Please note that invariant, that is epsilon x1 plus epsilon y1 equal to epsilon x plus epsilon y. Similarly, sigma x dash plus sigma y dash is equal to sigma x plus sigma y. Another invariant is given in your coursework to solve, in your assignment to solve, is sigma x dash into sigma y dash minus tau xy square is equal to constant. Not constant, it's equal to 0, I suppose. Okay. No, sorry, I'm mistaken. It's not 0, it's constant. So these are the things, few invariants that you have to find out from. So this is one invariant, this is second. All right. Similarly, for strain also, you can find the same thing. Here is the maximum principal strength and maximum shear strength that you can find out. The formulas are given here. So maximum principal strain, maximum minimum principal strain are given by this formula, where you can see plus minus. So the plus goes to maximum and the minus goes to minimum. The angle for which it comes is gamma xy by epsilon x minus epsilon y. See that here there is a 2, that 2 is missing here because this is gamma by 2 into 2, that 2, this cancels and become gamma xy. Similarly, maximum shear strain is given by this formula, which is radius of a Morse circle. We have seen that. And average, at that point, you will have average strain, which is gamma x plus gamma y by 2. Right? So if you want, if this picture we have shown in the last class also, that if you have an element which looks like this and draw a circle within it, then extension along one direction makes it an ellipse. Okay. Now in this ellipse, what are your principal directions? The principal directions are the center lines. Is somebody asking any question here?
Sorry.
But if you have shear as well as elongation both together, then this is one of the principal direction and that is one of the principal direction. So what, this is the maximum principal axis and this is the minimum principal axis, which are your maximum and minimum principal strengths. Okay, Morse circle. So finally we are into Morse circle. That is what we have to draw today. Like this shear, like the stress we have for strengths also we have Morse circles. And similarly, you can see that epsilon x1 minus, if you do this, so this is what? Whole square, that means this square plus this square. And then you do gamma x1 y1 whole square. So you add them up. And then this square, this whole square plus this whole square adds up. And if you do, you get something which is constant, which is independent of angle theta. This constant is called the radius of the Morse circle. Okay. So we have to do the construction. So this also, this equation is, this is, we don't write sigma x1. Yeah, sigma x1 is fine. And gamma x1 y1. So this is equation for a circle, right? And The center of the circle is this comma 0. That means x plus epsilon y by 2, which is average strain comma 2 is the circle, and these two are the variables in it. So let's draw it. Okay. Again, like last time we have done, we will see whether it's a anti-clockwise strain or not for the shear, or clockwise strain or not for the shear. If it's an anti-clockwise, that means it is going this way, we'll have it positive, and if it comes this way, we'll have it negative. Please note this. All right. And what will happen is we have to divide the strain that we have into two, right, to get strain on both sides. So at a point, the state of strain at a point is epsilon x, epsilon y, and gamma xy, right? So what we give is gamma xy, right? But when you want to write that in matrix format, you have to write it like this: epsilon x, gamma xy by 2, right? And when you write them as gamma xy by 2, gamma xy by 2, then you have to look at this is anti-clockwise and this is clockwise, right? So clockwise goes to negative. That means on the upper side of my axis, because my downward is positive, the anti-clockwise is positive. This is my positive gamma xy axis, and always the right hand side axis is a positive strain axis. Okay. So now let us look at this element. What is this element has? You see, this is my original element, and this is my deformed element, right? Now, original element and deformed element, there is no extension. Similarly here, original element and deformed element, there is no extension. It's parallel to this line, and this is parallel to this line. So there is no extension. Therefore, this point V, the axial strain is 0. Shear strain is positive gamma xy by 2. Similarly, this side, it's going to be CS normal strain is going to be 0, sigma y epsilon y is 0, comma minus gamma xy by 2 y minus, because it is this is clockwise rotation, right? So this is only shear given to the material, and if you give only shear, it's going to look like this, and this is what only positive shear that is given. So gamma xy is positive. That will have two kinds of rotation. One side will have a clockwise rotation, the other side will have anti-clockwise rotation. Therefore, if I want to plot this point point V on my Mohr circle, so what I'll do, I'll draw two axes here and draw a Mohr circle, right? For drawing the Mohr circle, I need this point. So this point is 0 gamma xy by 2. So this is my 0 epsilon x. Positive gamma xy by 2 is downside. So this is my gamma xy by 2. And then I got the radius. This is my 0 line. We call it 0 degree baseline. And we draw a circle. So this point you can see is the upper H point. It's 0 comma minus gamma xy by 2, which you know that if this makes an angle 90 degree, this makes an angle 180 degree anticlockwise, right? So that's your point H. Is that clear? Same thing has been drawn here with a negative shear stress, shear strain. There is a negative shear strain. So when it's a negative shear strain, the angle becomes more than 90. So this will be a deformed profile of the element, right? And we made sure there is no normal strain. So this point and this point matching, this point and this point matching. So there is no normal. Therefore, point V is, you can see this movement is clockwise movement, right? This is a clockwise movement, and this is an anti-clockwise movement. So clockwise movement is minus gamma xy by 2, and anti-clockwise movement is plus gamma xy by 2. So this is all right. So yes, so let us draw the Mohr circle. This is my axis for the Mohr circle. Now this point V is minus, right? 0 comma minus gamma xy by 2. So this is 0 and minus is the upward side. So this point is 0 comma minus x by 2. So I got a 0 degree baseline and I can draw the circle now. So this becomes your V point and this becomes your H point. Clear? I'll wait for a minute to digest for you to just check whether you are okay with it. Now, how to draw Mohr circle for a given state of strain? Okay, so let's say I have been given, let me rub this part. I have been given a state of strain at a point in a member as epsilon x, epsilon y, and gamma xy, right? This will be given to me. I will convert that into matrix format like this, epsilon x, epsilon y, and here I will write it as gamma xy by 2. Here also I'll write it as gamma xy by 2. Okay, let's say this represents my plane A, V, not A, and this represent my plane H. Okay, so that's the coordinates, right? So coordinates are given as, at V it is epsilon x comma gamma xy by 2, right? And at H it is given as, now you see, since it is positive gamma xy, right, I can draw the element like this here. So this is my plane, undeformed plane, and the deformed plane, since it is a positive gamma xy, one side it is going to be clockwise, the other side it is going to be, sorry, one side it is going to be anti-clockwise and the other side it is going to be clockwise, right? Therefore, the clockwise is at this plane, H plane, it is clockwise motion. So I'm going to write it as epsilon y comma minus gamma xy by 2. This is what we just showed with this example, right? When you have a positive strain, your one side goes to positive gamma xy, the bottom side, because there is anti-clockwise movement, and the other side goes to a clockwise movement, and that becomes minus gamma xy. But when you have a negative shear strain, then it's quite the opposite. Okay, so this goes to be minus gamma xy by 2. Let me correctly write it. Does it look good? Minus gamma xy by 2. Okay, now let's draw the Mohr circle here. So since you see both epsilon x and epsilon y positive, so I have to draw a positive, bigger positive axis here. So this is my positive normal strain axis, and this is my positive shear strain axis. Okay, all right. So this is positive shear strain, and that is positive normal strain. Now let us look at the points. So let us first plot point A, V, plane V. Now plane V has coordinates epsilon x and gamma xy positive. So both are positive, so it's going to be this plane, right? Both positive is this plane. So I'll go this way as gamma as epsilon x, and then I'll go down as gamma xy by 2, and I come here this point. So that's my V point. Now we have to look at plane H, which is epsilon y. Let's say I go to epsilon y like this, and then I go to minus gamma xy by 2, which will be upward, right? Go here. So that's my point H. Now I will just draw a straight line between point H and V, like I did in Mohr circle of stresses, right? I'll just draw and join them, and that point where it cuts the strain axis, normal strain axis, is my center C, right? This is my center. Okay. Now, what is my 0-degree baseline here? This is my 0-degree baseline. CV is 0-degree baseline. Once I know my baseline, that's my radius, and I can draw a circle. Okay, the values are very clear. This abscissa is gamma xy by 2, and from here to here is epsilon x minus average center, right? Center is average, so this point is C. C point is given as, what do I write? Is epsilon average was 0, right? What is epsilon average? epsilon x plus epsilon y by 2. Okay, so that's my center. So this is going to be epsilon x minus this guy. Okay, so this is what you get, and you can draw the circle. Now this circle will cross 2 points P1 and P2 on the zero shear stress line. That means your plane stress line, plane strain line. So these are the 2 points. So one of them is corresponding to maximum principal strain. The other will correspond to minimum principal strain. The angle that it makes with your 0-degree line is called 2 theta p. Is the gives you the plane of the maximum principal strains. Similarly, you have to find maximum principal shear strain. So maximum shear strain, not principal stress, maximum shear strain. So this is your maximum shear strain. Okay, gamma xy max. Okay, and since the axis is gamma xy by 2, this, remember that this axis is gamma xy by 2. So this is gamma xy by 2 max. Okay, not gamma xy max. So double of that is the maximum shear strain that you're going to have. All right. So this is how, and the angle for that you can find. This is my theta s. Okay, and theta s is given by theta p plus minus 45 degree. All right, or that is also equal to tan inverse minus epsilon x minus epsilon y by gamma x. This minus is outside, right? This is what we have seen in the last class. Okay, so that's how you draw Mohr circle, and once you draw the Mohr circle, you can find out whatever values you want and at whatever angles the values you want. Okay, same thing as principal stresses. We have salient points here that at along principal strains, along the axis of principal strains, there is no shear strain. Okay, no shear strain as those planes. Similarly, in case of maximum in-plane shear strain that you have, which is the radius, you get average normal strains, same as stresses. And element representing makes an angle of maximum shear strain makes an angle of 45 degree with respect to the principal planes. Okay, with respect to the principal strains, sorry, principal strain planes. Okay, now how do you draw the deformed configuration? I've told you already how to draw deformed configuration, and I will not going to explain it again today. What I'll tell you, please go through this. I've given step by step how to draw the deformed configuration. So all the steps are given here, and that the same steps are used to draw this figure. Okay, so please go through this, and if you have difficulty, please come back to me. I have already explained it in the last class, so make sure that you go and practice this. Okay, last class we solved one problem. Let's solve another problem today. Transformations that we have here. What it says that a differential element is shown here. So this is the differential element. Subject to a state of plane strain, the plane strains are given. That is sigma epsilon x is 500, epsilon y is 300 minus, and gamma xy is plus 200. Okay, so they can also be written as 500 micron minus 300 micron, 200 micron. Okay, that's my strain. So what I'll do is I'll divide gamma xy by 2. So gamma xy by 2 is equal to 100. And as you can see, it is positive. Since gamma xy is positive, I will have this plane moving anti-clockwise and this plane moving clockwise, right? So, and there is epsilon x positive. So epsilon x positive means this point goes elongated like this. Therefore, this line will be more than this line, and you know the rotation is gamma x1 by 2. So this point comes out to be this line, comes out to be this line. Now about epsilon y, it is negative. So this is going to compress and come down a little bit down here. And then there is a clockwise rotation, because positive shear will give a clockwise rotation at the of the y plane. So this is goes this way. So it makes a little down here. So this is the line. And this line, therefore, the y line therefore becomes this y dash line. Okay. So this is my line. Now what you have to do, I have to draw a parallel line. Parallel to this line, I will draw another line here. And parallel to this line, I'll draw another line here. They will connect at this point. And therefore, this is my deformed element of the point. Now it has been asked that determine the equivalent strains acting on an element or material oriented at a clockwise 30 degrees. So it's a clockwise 30 degree, right? So I know the formulas. I can just put the formulas. So that's my formula. Epsilon x dash is going to be epsilon x plus epsilon by 2, epsilon x minus epsilon by 2 cos 2 theta, and gamma x by 2 sin 2 theta. That's my formula. I have to put theta equal to 30, so that becomes 60 here, and that becomes sin 60 there. And once you do all the calculations, you get 213 10 to the minus 6 as your epsilon x dash. And similarly, gamma xy, how are you going to do? You just put the values back here again. You get 793 into 10 to the minus 6 as gamma xy. But we still need to find epsilon y dash, right? How are you going to find epsilon y dash? This is how you find epsilon y dash. Okay, what you can do, another way of finding is easier way. Please note this. It is useful for small objective type questions, right? So epsilon y dash, epsilon x plus epsilon y minus epsilon x dash. So it's much simpler than doing this. Or you have to put, much simpler than doing that. So this is what you do, and you will get epsilon y dash. See, epsilon y dash is minus of something. Now we have to draw the element. How do you draw the element? So this was my, I've already known now. I know epsilon x dash, I know epsilon y dash, and gamma x dash y dash are known. Right now, after solving that, so I will have one axis. This is before transformation axis. After transformation axis, that is 30 degree clockwise. So I'll make this axis move 30 degree clockwise, and this becomes your transformed axis, right? So my element will be now on this axis. So I draw an element on that axis. This is my element on that axis. Okay. Once the element is drawn, I have to give the deformed configuration to it. And we know the deformed configuration, epsilon x dash is positive. So it's going to elongate like this. Gamma xy is positive, you see. That means along x-axis, it is going anti-clockwise, and along y-axis, it's going clockwise, right? So I'll write that also here. Gamma is positive, meaning along OX, it is anti-clockwise rotation. Gamma x by 2, and clockwise along OY or okay, that's clear. So what I get is this line rotates clockwise to this, and this line rotates anti-clockwise this. So there is a positive value, so there is an elongation here. There is a negative value in epsilon y. You can see negative value here. So it's a compression a little bit. So this going to become this, and then you have to draw parallel lines, right? Just parallel lines, and then you get this point. So that's your deformed configuration in a rotated coordinate axis or a transform coordinate axis. Okay, right? Problem 3 is similar. You can do it yourself. Please check and do it yourself. If you have done strains and stresses and you have gone through so many problems, you will be definitely do that. Once you have problems, please come back to me and I will be definitely happy to help. This is not, and also try to check whether you get the answers that I have provided here. So this is transform profile. Okay, deformation also in the transform coordinate. Okay, Mohr circle. The state of strain is represented by the components determine the principal strains and the orientation. So you have been asked to find the principal strains given a state of strain. Say epsilon x is given, epsilon y again you see negative, and gamma xy is given. So what I have to do is I have to take point A. Point A is going to be epsilon x comma gamma xy by 2, positive, because that's positive here. And point, let's say this is point A, B, C, D is given. Let's say this is H. Point H is going to be given as epsilon y comma minus gamma xy by 2. And if I do that, first I have to choose the A point and I have to draw my line. So A point is this 250 comma plus 60. So this is my A point and that's my 0-degree line. Okay. Before that, I can find the center. The center can be epsilon x plus epsilon y by 2. That is this 50 center point. And I can draw this line. Or else I can find h also, which is epsilon y minus 60. So minus 150 and minus 60. So this is the point. So you can then join them like this. Okay. So that's how you draw the Mohr circle. So this is my 0 line. Now I can find my planes, principal planes. So this is my 60. And that's my 250 minus the center point. So my center point is 50, 250 minus 50 is 200. So this is known, you can find the angle that is given here. And then you can also find the maximum shear strength by just joining the another diameter. So this is your maximum shear strength. Gamma by 2. Okay, max. Measuring strain is a challenge in the sense we cannot see strains, we can see deformations. So what we do is we measure deformations and then convert them to strain. So either you can use to measure deformations, you can use one is laser displacement sensors. Okay, laser sensors you can use to measure the deformation. What it does is, if you have, let's say I have a beam here, and what you do is you point a laser to some point here, let's say some point there. I am putting a laser here. Okay, so when it deforms, let's say it deforms in the other direction, this laser will calculate it, right? How much it has deformed based on the change in the position, whatever position P is there. So that's how you can, so this might be your 0, and then you can calculate this. So the laser sensor gives you how much deformation it has. Apart from that, there are something called strain gauges, which are used to calculate strains. What a strain gauge does is, these are material mostly made up of piezoelectric material, mostly piezoelectric materials. There are many more materials nowadays which they are not commercially available, but which can also be used to calculate deformations or strains. But let us go with piezoelectric, piezo-composites, we call it, piezo-composites, which are used to make these strain gauges. So strain gauges are mostly piezo-composites, and within which there will be electrical circuit like this. There are various ways. One of them is this. There can be interdigited circuits like this. Then this, something like that, interdigited. Sometimes, there are various combinations. Okay, now what it does is, when you paste it to a material, okay, the material will elongate under a strain or deform under a load, And when it deforms, it will pull this member, and this member will elongate, right? And when it elongates, it produces electrical charge. And that electrical charge is picked up by these circuits here. Okay, copper coil or something will be there, electrodes, and those electrodes will pick up those and will send back to the reader, maybe a meter which reads it, or maybe a computer which reads it, or maybe a DAC system which can read it. Okay, digital acquisition system. And that's how it works. So strain gauges are used to measure strains in materials. And it was like you guys, some undergraduate to postgraduate, I think, who made these strain gauges first time in MIT. I think maybe 80 years old or something. So the understanding makes this kind of potential devices. So this is a strain gauge. Now, as I said, it only measures strain along a particular direction, which is along its axis. Okay. How many number of unknowns we have in a point, at a point in a material? In a 2D material, we have epsilon x, epsilon y, and gamma xy. Okay. So there are 3 unknowns. So I need 3 equations to solve, right? I cannot solve it with 2 equations. I need 3 equations representing all these 3 to solve these 3 points at a point, right? So these are the 3 equations. So what I need is, I need 3 strain gauges to find. So each strain gauge will give me 1 data. So I need 3 strain gauges to solve a problem, and they cannot be along a single line. They have to be on a different direction. So let's say this is my epsilon 1, this is my epsilon 2, and this is my epsilon 3. These are the 3 strain gauges that are there. Somebody writes it as epsilon A, epsilon B, and epsilon C, whatever you want to write. We can also write it as epsilon A, epsilon B, and epsilon C, because sometimes epsilon 1, 2, 3 are represented for maximum principal strains, right? So we can write this as A, B, and C. This also A, B, and C. So we need 3 strain gauges to be connected near a point. So they all should connect to a point, but not far away from the point. And they will give me 3 values, right? All these 3 values I can represent in my strain transformation equations. And they will have the unknown strains like sigma x, sigma y, epsilon x, epsilon y, and gamma xy. And then we can solve it, right? Solve these 3 equations to solve my unknown epsilon x, epsilon y, and gamma xy. Okay, so there are 3 strain gauges that are needed, and this strain gauge I can plant it as I want. So a few of them are easier to solve, and they are available. Remember that you may not always paste it as a directions you wish, because the geometry may be very complicated, and in that case you cannot get all the angles that are always 45-degree making or always 60-degree making. So you have to calculate this angle. So a general angle is theta A, theta B, and theta C, right? So this is called 45-degree or a rectangular rosette, and this is the 60-degree strain rosette. Now I can put these values of 45 into these equations and find the simpler relationship, right? So let's look at 45-degree strain rosette. My angle theta A is 0. This is along the x-axis. Angle theta B is 45, and angle theta C is 90. So when I put this expression back here, so let's say theta equal to 0. So this becomes 1, this becomes 0, and that becomes 0. So epsilon A is equal to epsilon x. So epsilon x, your x direction unknown strain, becomes equal to epsilon A. Similarly, you can put those values back, and you will get epsilon y is equal to epsilon C, and gamma xy is given by epsilon B minus epsilon A plus epsilon C. So half of this. So this is a very easy relationship that you get. Similarly, for 60-degree rosette, you can put it back and find the equations, and these are the 3 relations that you get. So you can use directly these relations to solve the problem. Now, we have to solve one problem related to this. So objective here is, you have a material body. Okay, you have a material body, something like this. Let's say I have a body like this, and I want to find strain here at this point. So my unknowns are epsilon x, y, and gamma xy, right? These are my unknowns. Therefore, what I'll do, I'll put strain gauges along this. So I can put So let's say my XY axis are also like this. X, Y. This is my rotation axis. Okay. So what I can do, I can put my strain gauges as I want, maybe one along this direction, one along this direction, one along this direction, right? And they give me some values. Let's say this gives me epsilon A value. When I do measurement, this is epsilon A, epsilon B, and epsilon C. Let's say this angle, we put it as 45 degree. Now you know epsilon A, epsilon B, epsilon C. You put those values back into this expression. Then unknowns in these equations are epsilon X, epsilon Y, and gamma XY. These three are unknown because sigma ABC are known. Sorry, theta ABC are known. They are given by the expression 45 degree and 90 degree. And these three are obtained from measurement. You'll get a matrix, invert that matrix, and you'll get epsilon X, epsilon Y, and gamma XY. That's the objective of having strain rosette. So this is a similar problem given here, which you can solve and do it. Okay, I'll probably do another problem here. Yeah. So this is the material body. It is under various loading. What is been asked is there is a point A where there are strain gauges attached at A, B, and C, and they make an angle 60 degree and 120 degree like this. So this is a 60 degree strain rosette. Okay. And the values that you obtain from epsilon A is this, strain gauge A, strain gauge B is this, strain gauge C is this. Measuring the angles in a counterclockwise direction. So epsilon theta A is 0 because that's along the x-axis. Theta B is 60 degree and theta C is 120 degree. I know all these values and I will put it back into my expression. The expression was, the expression was this one for 60 degree rosette. So my epsilon X becomes equal to epsilon A, epsilon Y you have to calculate, and gamma XY also you have to calculate in terms of epsilon B, epsilon C, and epsilon A. So you can calculate them. Once you calculate, you get this. Epsilon X is this, epsilon Y is gamma XY is this. Once you know them, you can draw the Mohr circle, and once you draw the Mohr circle, you can find the principal strains that are needed. So this question asks you to determine the in-plane principal strains, right? So you can find the principal strain once you know the one of the plane. So one of the plane is given by this magnitude. So this is one of the plane. This plane you can draw in the Mohr circle. So I've just drawn the Mohr circle as it has to be. So this is 60, and this is 149 divided by 2, 74.5, right? And this is negative. That means going to be upside. So this, okay, is my 0 degree line. So now you can find the plane. So, and this C is given as epsilon X, comma 0. So epsilon X is this, epsilon Y is this. You can add them and divide by 2, it gives you center, and you can draw this 0 line. Once you draw the 0 line, you can get theta P, and that is an anti-clockwise some 2 theta P degree, which you can calculate with the help of a protector, and then you can tell that values here. And then you can draw the plane also, deformed plane. So with that, I'll stop. There is another here which you can do yourself. As I said, there can be complicated structure, so you can find strain here, but not here. It will be very difficult to find strain along this line because it's a curve. Okay. With that, I'll stop.